Welcome, my Calculus AB students, to your first video lesson with Mr. Smith during our distance learning session here. I hope you've all been working on your previous assignments about the integral review sheet. Many of you have sent me pictures of what you've done and checked in with me, and I appreciate that. And hopefully my suggestions over email were able to help you finish the rest of the problems. I will post solutions to those soon. I did post solutions to the first homework that hopefully you checked, and I'll post solutions to the integral review sheet in another day or two. I'm still waiting to get some work back from other students in the class. So if you haven't done that yet, please get that to me soon. We do need to move on with Chapter 8. Now, this is the last chapter we have of our new materials for this curriculum before we begin reviewing for the AP exam. And Chapter 8 is all about applications of definite integrals, right? And as I think I mentioned this a little briefly last Friday before we left, that 8.1 is going back to physics examples and other examples as well, not just physics, but that's a large part of it. Anything having to do with accumulation or net change. That's what 8.1 is about. And then after this, we'll get into area and volume problems. But let's start with this here today. I want to begin by going back and reviewing the fundamental theorem of calculus, how we evaluate definite integrals. So if we have an integral from a to b of f prime of x dx, we know we do the antiderivative of this, evaluate b and a, and take the difference. Well, the antiderivative of f prime is just f. So this is just f of b minus f of a. Okay, so we're all very familiar with that. Now, we can rearrange this, use just a bit of algebra to rearrange this and solve for f of b. Okay. If I want to get f of b by itself, I would add f of a to the other side. So I can write this as f of b is f of a plus the integral from a to b f prime of x dx. So what this is saying then is that if you have a derivative of a function and any point, any y value, you can find any other, you can find the y value at any other given x coordinate. So if you know f prime of x and the value at a, you can find the value at b by doing this, f of a plus the integral from a to b of f prime of x dx. Now, you've already done problems similar to this, just phrased a little differently. You've solved, this is basically the same as solving a differential equation given an initial value. You take the antiderivative, you plug in your initial value to find your c, plug your c back in, and then there's your value of the function. All right, and then I can plug in whatever value you're given to find that. This is basically doing the same thing, just phrased a little differently, written a little differently. But still, you have a derivative here, and you have an initial value. So all this is saying is that if you can find the integral from a to b of the derivative and add the initial value, you get the final value, if you will, or f of b. But this is at a specific value b, so this answer will be a number. We can also rewrite this to get a general function from its derivative, that f of x is f of a plus the integral from a to x f prime of t dt. Now notice I had to change the variables here by variable integration from x to t as a dummy variable, since this x goes with this x. Okay. But this is what we're going to be used so many times. And actually what we're going to be doing here in our physics examples for a moment comes right back to this. If I have a derivative and initial value, I can always come up with a function. Okay. So as I said, this is really just like solving a differential equation given an initial condition, just written out differently. Instead of given dy dx, you do the antiderivative and plug in your point to find the c, it's writing it out using a definite integral. But mathematically, you're doing the exact same thing. All right, so as I said, keep that in mind when we come down to what we're doing here in a little bit. We can apply that to physics now. If I want to find the position function, well, if I know the velocity at any time t, the velocity is the derivative. So if I know the velocity and an initial position, I can find any other position. So I can just take this and rewrite it in terms of s and b instead of f and f prime. So I can say s of t is s of a, whatever initial value given, plus the integral from a to t of the derivative position, which is velocity. So v of x dx. Now here my variable of the function is t, so I'm going to put this in terms of x. But please look back here. Notice the similarities. It's the exact same math that you're writing, just different notation. This is the physics specific way of writing this general thing. But v is the derivative of position. So you're saying the exact same thing as above. All right, so what that means is if you have a velocity function and initial position, you can always find the position function. All right, now, what is displacement? Displacement is the change in position from A to B. So again, it's not how far you moved, just where are you at A compared to where are you at B. All right, and the way we write that out then is S of B minus S of A, right? Your final position minus your initial position. Well, this should look familiar, right? Go back up to the Familiarity calculus. F of B minus F of A is the integral from A to B of F prime of X. So what this is saying is that displacement, S of B minus S of A, is simply just the integral from A to B of the derivative position, which is velocity. So if I integrate the velocity function from A to B, I get the particle's displacement. And those of you in physics have probably already known that and used that before. Where the area under the curve is displacement. If you have the velocity curve, area under the curve is displacement. Well, the area under the curve is a definite integral. Now, what about distance traveled? Distance traveled is a total distance traveled in either direction. So distance traveled is always positive. Displacement, again, can be positive or negative. Distance traveled is always positive. So distance traveled is the integral from A to B of the absolute value of velocity. Okay, it's the integral of the absolute value of the function. So distance traveled is very similar to area under the curve, right? Remember we talked about area. Area is always positive, right? So if you have a curve where some parts above the x-axis and some parts below. If I want to find the displacement, let's say this was velocity. If I want to find the displacement, I would do the area above minus the area below, right? Because this integral is positive, so this would be moving to the right. This integral would be negative, moving to the left. So displacement would be this area minus this area. That would be displacement. Distance traveled is the total distance you travel in either direction. So distance traveled would be this area here plus this area here, which again is also what we call the area under the curve, where you find each of these integrals and add their absolute values. All right, so that is the difference there between displacement and distance traveled. Now, one more thing. I can take what I did here for position and do the same thing for velocity, right? Because velocity is the derivative of position, acceleration is the derivative of velocity. So if I know the acceleration function and the initial velocity, I can find the velocity function by writing it the same way. It's going to be v of a plus the integral from a to t of the acceleration a of x dx. Okay. Now, my notation is kind of bad here because this a and this a are different. So maybe I should use a different letter, right? This a is an x value, a lower bound, where this a stands for acceleration, the derivative velocity, just to be clear on that. All right. So there's a lot of times on free response problems or even multiple choice problems at AP exam that they give you physics problems as applications, okay, both either derivatives or integrals. So let's look at some examples of that. We're going to do this one example together, then I'm going to give you a couple examples to try on your own and see how that goes for you. So first one here, given the velocity of the particle, so this is linear motion. Again, assuming horizontal velocity back and forth. Here's the velocity function from 0 to 5. Now you are definitely going to want your graphing calculator for this. So you might want to take a moment to pause this video, get out your graphing calculator, and type this function into graph it just to get a visual for the velocity curve. And while you're doing that, you can answer part A. So you can wait a moment if you want to pause the video and get out the calculator and graph that. And then come back when you're done. So once you have this graphed, you want to find the initial velocity, okay? Anything initial is always just time t equals 0. So just plug in 0 for t, and you get -8, and that'd be 7 meters per second. Part B, find when does the particle change direction. Change direction meaning when does it go positive to negative or negative to positive, okay? And we can see that starts out initially velocity is positive, so when does it change back to, velocity is initially negative, when does it change back to positive? Well, on the velocity graph, that would be when it crosses the x-axis. So just find the x-intercept, in other words, set velocity equal to 0, find the x-intercept, okay? And just to be clear, I'm only looking for values between 0 and 5. So if it changes to the left of 0, I don't care. I just care about values between 0 and 5. So find the x-intercept between 0 and 5, and you get approximately 1.255 seconds. So from 0 to 1.255, velocity is negative, it's moving to the left. And then after 1.255 to 5, velocity is positive, it's moving to the right. Next question, find the displacement from 0 to 5. Displacement, remember, is simply just the integral of the velocity function. So integral from 0 to 5 v of t dt. Okay. And this integral you can do in your calculator. Now you could do this by hand if you wanted to. This is an antiderivative that you should all be able to do by hand. But as I said before, with these application problems, these are almost always with a graphing calculator. So just type this velocity function that's on your calculator, just integrate that from 0 to 5, and you should get 35 centimeters. So that is the displacement. That's the change in position from 0 to 5. Not the distance to travel, the change in position. All right. Find the position function given s of 0 is 9. Okay, so now I have an initial position. Now I can find the position at any time t. So if I want to find s of t, the position function. Okay, again, just to be clear, I'm going to go back to the front page here. I'm doing this right here. If I have the velocity and initial position, I can find the position function. So it's just going to be s of 0 plus the integral from 0 to 9 of the velocity function, v of x dx. And again, I'm going to change the since it's t, I'm going to put that in terms of x. And s of 0 is not I'm sorry, that should not have been a 9. I'm sorry, that should have been a t. That t goes with that t. I was one step ahead of myself. S of 0 is 9. Sorry, the 9 is supposed to go here. So I can plug in 9 for s of 0. It's going to be 9 plus integral from 0 to t of the velocity function. All right, now for part E, now let's find the position at t equals 5. I believe your handout says t equals 1. That was a typo on my part. It's supposed to be t equals 5, so please change that to a 5. Find the position at t equals 5. So we just plug 5 in for t above. S of 5 is going to be 9 plus the integral from 0 to 5 of the velocity function. But we already did that above, right? The integral from 0 to 5 of velocity was right here. That was the displacement. So it's just going to be 9 plus 35, so it'll be 44. So at after 5 seconds, the position is 44. Okay, so, and I want you to take a moment, just kind of think of this sort of logically, not even just with calculus, but just think what this is saying. This is saying that the displacement from 0 to 5 was 35 centimeters. That's how much they moved, a total of 35 centimeters. So if they started at 9 centimeters, if you wanted to know where they after 5 seconds, you would simply just add the 35 to the 9 and get 44. Okay? Now, finally, part F, find the total distance traveled from 0 to 5. Now, total distance traveled is integral from 0 to 5 of the absolute value of the velocity function. Okay? So total distance traveled now, again, doesn't matter if you're moving left or right. I want to know what is the distance they moved to the left between 0 and 1.255, and the distance they moved to the right from 1.255 to 5. I'm going to add those together. But you don't need to do that manually. You can just type this in your calculator, let your calculator do the work for you, and you get approximately 42.587 centimeters. Okay, so that's how much that particle traveled during those 5 seconds. Now, if you flip the page, the next 2 examples, I want you to work on these on your own. Okay, this is going to be your first homework assignment. These are problems I copied from other practice exams, practice AP exams. And this is exactly the kind of questions they will ask on the AP exam about these, giving you a velocity and then giving you an initial position. So notice, it doesn't have to be at 0. This is position at t equals 2 is 3. Giving velocity tells you position 2 is 3. Answer these questions. Okay. Now notice, you don't need the 3 to answer all of them. Sometimes you do, sometimes you don't. Okay, so just, again, pay attention to what's asking. If it's simply asking for displacement, change in position, the initial position doesn't matter, right? Does not matter, right? But if it wants to know what's the final position, that's when you want to use the initial position. So just, again, pay attention closely to what's asking, and look back at the previous examples. There should be similar type of questions. And same for example 3. All right, example 3. Another one, it gives you an acceleration function, and then it gives you the at t equals 0, the velocity of position. So you know the acceleration, you want to find both the initial velocity, or sorry, you're given both the initial velocity and initial position. Okay, so you want to find the velocity function at time t. Okay, and now that you want to, you can initially write as integral if you want, but you want to actually find the antiderivative. All right, you should be able to do that antiderivative without too much trouble. So find the velocity function in function form without an integral. All right, because you're going to need that answer in A to answer parts B, C, and D. So once you get your velocity function A, answer B, C, and D. Okay, so why don't you try 2 and 3 on your own, and I will post the solutions to those in another day. All right. Now, example 4. Let's do this one together. All right. So this is going back to where I talked about at the very beginning. All right. Just a generic derivative, not necessarily a velocity, but it's the same concept still, but just a generic derivative. I'm given a derivative and an initial position, or initial value, excuse me. I'm used to physics terms here, sorry. If I'm giving a derivative and initial value, I can find any other y value. So this time I'm not given an equation for the derivative, I'm given a graph of the derivative. But that's okay, because I know I can use the graph to evaluate the integral. All right, so I'm given f of 0 is 9. Find each of the following values. Find f of 2. Okay, so let's go ahead and write this using what we wrote on the first page. Okay, and everybody, I want to make sure you write this down. Write it down as the integral before you plug in any numbers. I want to make sure you're clear what we're doing. All right. You know the value at 0. I want to find the value at 2. So start with f of 0 plus the integral from 0 to 2 of the derivative, f prime of x dx. Okay, so again, just to be clear, the value you know goes here. The x value you want to find goes here. Okay, now this integral I can evaluate from the graph, right? I know that the integral from 0 to 2 is just going to be right here, the area of this shaded region, right, under the graph from 0 to 2. That area right there. Okay, so that value is 9 was given to me. And what do we have? Well, we have a rectangle and then a quarter circle on top of it. The rectangle is 2 times 1, so that's 2. And then this is 1/4 a circle of radius 2. So 1/4 pi times 2 squared. All right. And what do you end up with? That would be 11. If you write 11 plus pi, I wrote my pi a little too soon there. Good thing I brought my whiteout home with me, right, folks? 11 plus pi. So there we go. F of 2 is 11 plus pi. All right. Now, I want you all to do the same thing to find f of -3. All right. And like I said, and then I want you to try this one on your own. So everybody take a moment, pause the video, and right here, and I'll do the answer in just a moment. So just pause the video and look back at example A. Follow the same thing for example B. Okay, hopefully you are done with your example, and then you can check your answer with me. So let's write this out. This is going to be f of 0 plus the integral from 0 to -3 of f prime of x dx. Okay. Now, be careful. What do we notice here? This is written backwards, right? Because this value is less than 0. My lower bound is larger than my upper bound. Okay. So we know from our rules of integrals, right? We can flip that around and make the integral negative. Okay. Or take the opposite sign, because it could be positive. So I can do the integral from -3 to 0 and then subtract it from f of 0. All right. So once again, I'm going to f of 0 is 9 minus, and then I need to find this area right here from -3 to 0. Well, symmetry tells me I already did this area from -2 to 0, right? I know it's 2 plus pi. Okay. Then I just have to add this little triangle here, which is area of 1/2. So it's going to be 2 plus pi plus 1/2 is being subtracted from 9. Okay. And 9 minus 2 is 7. 7 plus 1/2 is, or 7 minus 1/2, excuse me, is 13/2. So there you go. F of -3 would be 13/2 minus pi. Hopefully that's the same answer that you got on your own. Lastly, now, what's the second derivative of 3? Okay, well, this is the first derivative. This graph of f prime. So if I want to find the second derivative would be the slope of the first derivative, right? The slope of f prime. So I want to find f double prime of 3, go to 3. What's the slope of this line right here? Well, that's simply just -1. Okay, so these kind of problems right here like to show up in the AP exam at a free response, where they'll give you a graph of a derivative, because they can ask you questions both ways. They can ask you questions about the original function using the integral. They can ask you questions about the second derivative using the derivative. So you've got both branches of calculus combined into one problem here. Okay, so that's a good kind of problem to try. I'll give you more of those to practice as well. Okay, but I want you to one more time just notice the similarities between what we did here in general function terms compared to what we did previously with our physics problems. All right, last one here, example 5. Okay, now notice the beginning of the chapter, the section was titled Accumulation and Net Change. So any sort of accumulation, you can use a definite integral. It doesn't have to be just a physics problem like velocity. Accumulating velocity is position. Accumulating acceleration is velocity. But any sort of accumulation problem, if you are given a rate of change, anytime you are given a rate of change, a function that's a rate of change, and you want to find the total amount of change over some interval, you always set that up as a definite integral. All right, so here's an example. From 1970 to 1980, the rate of potato consumption in a certain country was this right here. CFT is 2.2 plus 1.1 to the t millions of bushels per year. And we know it's a rate of change because it says per year right there. Where t is the year since 1970. How many bushels were consumed from the beginning of 72 to the end of 73? So I want to find the total consumption of potatoes. Okay, total consumption. Well, this is the rate of consumption, right? This is how fast the potatoes are being consumed, millions of bushels per year. So anytime I have a rate, I want to find the total value, I simply do a definite integral. So I'm going to integrate 2.2 plus 1.1 to the t. Now, what's my upper and lower bound? Well, let's see. I'm starting in 1970. That was t equals 0. So beginning of 7, and we're assuming the beginning of 1970 if it doesn't say otherwise. Beginning of 72 would be 2 years later, t equals 2. Now notice, be careful. It says the end of 73. Well, the end of 73 is the same as the beginning of 74. So the integral would go from 2 to 4, not 2 to 3. The beginning of 72 to the beginning of 74. So integrate that from 2 to 4, and you get about 7.066. So what are the units? Well, that was millions of bushels per year. I multiplied it by years, so that's simply just millions of bushels of potato. All right. So anytime you're given a function that's a rate of change, and you want to know the total amount of change, you can just use a definite integral. All right, so your book has a couple of homework problems we'll get through later about that, where they give you, now they could give you the function and the equation for the function, or sometimes if you don't have an equation, you'll have a set of points, and we can approximate that integral with the Riemann sum or trapezoids or one of the things we've done in the past. Okay, so there's various ways we could do that. All right. Now, flip to the last page. Here's another example. What I just talked about. Water is being pumped into a tank at a rate given here. So this is a rate of change. Gallons per minute, this is a rate. But notice, you're not given an equation of the function this time. You're given a value at 5 minutes intervals from 0 to 60. So we can't find the exact value of the integral, but we can approximate it with a rectangles or trapezoids. In this case, trapezoid sum. So that's what example 6a says. Use a trapezoid sum to approximate how many gallons were pumped during that hour, and then if there were initially 5,000 gallons of water, find the amount of water in the tank at the end of the hour. What was the average rate at which water was pumped out? And then was there a time during the first 20 minutes when this turned to 0? How do you know that is true? Okay, you've been asked a question like that before, so that should look familiar. All right, so I also want you to do example 6 on your own. So after we're done with this video, then and wrote down these examples and thought about them, I want you to try examples 2, 3, and 6 from this handout, the 3 that I did not do. And I'll give you another day to work on that, and then I will post the answers to those for you to check. And then after that, then I have some other problems from the textbook for you to work on. All right, so have fun with that. As always, email me or post a comment on the Google Classroom if you have any questions.